Okay, so back in Algebra 1, you learned the definition of a function. So this is going to be, I have that definition for you down at the bottom. You're probably going to want to write that down in your notes, especially if you forgot it from Algebra 1. So each x can only be paired with one y. So oftentimes it's easy to help you understand the definition by actually looking at something that's not a function. So this middle one is b is not a function. Did anybody remember that, by the way, from Algebra 1? I'm just curious. Okay. So what makes it not a function is, remember the definition says each x can only be paired with one y. So here's where it fails the definition. We have the x of 2 paired with 3, but you also have 2 paired with 5. That's no good. Each x can only be paired with one y, okay? If you look through, like, another way to think of it is like the x can't repeat. So over here, there's no repeats. Each x value is unique. You can shut that, Brenna. Like you have -1 paired with 3.25. You don't see -1 later on paired with something else, okay? On D, if we get the y by itself, like subtract x from both sides so that we could have it to go graph in our calculator if we want, you would see that it's, I'm actually going to write it this way with the -3x first and then the 5. Do you guys remember good old y equals mx plus b, I hope, from Algebra 1? This equation that I just wrote, -3x plus 5, that's a linear equation. The y-intercept of it is 5, and then it has a slope of -3. So it looks something like that if we graph it, okay? When you look at the graph, so it's very easy to tell if something's not, sorry, Emerson, I thought that was everybody. It's very easy to tell when something's not a function when you have a table of values. When you have a graph and you're trying to figure out if it's a function or not, we have something called a vertical line test, which your teachers might have mentioned to you in Algebra 1. So the vertical line test says if I draw a vertical line and it only touches the graph at one point, that's good. It would make it a function. So you have to be able to draw the vertical line anywhere, and it should only touch at one point. So A would be a function because it passes what we call the vertical line test, and so is D. If I draw a vertical line, it only touches the graph once. I'm just going to show you a quick example of a picture that would not be a function. If you graphed like a circle, that wouldn't be a function, because do you see when I draw a vertical line through it how it touches the graph more than once? That will be bad because you'll have the same x paired with more than one y. Like this could be like 2, 4, but this would be like 2, -4. Remember we said that's not good if you have the same x paired with more than one y, okay? So that's an example of something that we say fails the vertical line test. If you draw a vertical line and it touches the graph more than once, that makes it not a function, okay? So B was the only one that was not a function. Quicker. So we are starting 3.4 today, and 3.4 is going to be all about inverse functions. So first thing, we have some definitions here that you're going to want to write down. So basically, you're going to want to write everything on this slide. In an inverse relation, the x and the y are going to be reversed, okay? Another way to think of it, input and output are other words for x and y. So you could think of it that way. The input and output are going to be reversed. And then domain and range, we've been working a lot with domain lately. Domain is the x values that appear in a function. Well, in case you forgot, range is the y values. So basically all those like x, input, domain, those are all words for the same thing. So in an inverse relation, they're going to get switched, okay? You'll see what I mean by that in a minute. So this is something to know too, like you're going to want to write down that note at the bottom of the slide here. When you graph a function and its inverse, they're going to be reflections of each other over the line y equals x. I will show you what that means in a picture in a second. You just need to get it written down for right now. Okay, when I show you the picture on the next slide, we need to, again, remember a little bit from Algebra 1 here. I want to talk to you about the line y equals x real quick. So remember again, slope-intercept form that I mentioned on the very first slide, y equals mx plus b. I hope you remember that from Algebra 1. So if you just have the equation y equals x, it means m, the slope is 1, and the b, the y-intercept is 0. So I want you to imagine what that line's going to look like. It's going to start at 0, and remember slope like rise over run, it's going to go up 1 and over 1. So like it's going to look like this when you see a graph of the line y equals x. Okay, so when I go to the next slide, what you're going to see is going to have that line in it, okay? And then I'm going to show you actually a non-math example for a minute, okay? So if I have the green line that's there is the line y equals x that I was just telling you about. So part of your definition said that if you graph something and it's inverse, there are going to be reflections of each other over that green line. That means like a mirror image. So can you imagine if I took this and flipped it over the green line, how it would end up right here? Okay, that's what you're looking at right now. So that will happen with anything that you graph in math. If you have a function and you find its inverse and you graph both of them, they're going to be like mirror images of each other over this line, specifically the line y equals x, okay? All right, so we're going to start with a function where it's just, or a relation where it's just a set of points. So no graph yet, okay? So based on our definition, an inverse function is going to switch the x and y. So like see how the first point in our relation is 0, 6? So its inverse would be the point 6, 0. If we have 1, 4, the inverse is going to be 4, 1. You're literally just switching the x and y. If you have 2, 2, when you switch it, it's still going to be 2, 2. If you have the point 3, 0, when you switch the x and y will be 0, 3. And then when you have 4, negative 2, if you switch it, you're going to get negative 2, 4. Okay? So on the next slide, I'm going to show you a picture. If I were to graph all of these points, and they're going to be in blue on the next slide, and then I go and graph all these points, they should be, again, mirror images of each other over that green line that we were talking about earlier, okay? So let's take it one point at a time. If I graph 0, 6 and I graph 6, 0, here's 0, 6, here's 6, 0. Focus on just those 2 points and this line. Can you imagine that if I flip this over this line, it's going to end up right here, okay? So we could look at each pair of points individually. It's going to happen for all of them. Like the mirror image of this red one is this blue one down here, okay? That's always going to happen. When you have the inverse of something, it's going to flip over the line y equals x. It's going to be a mirror image, okay? All right, so we started out with a table of values. What if we have something given, a function given to us as an equation instead? How will we find the inverse? Well, here's the directions. I would recommend writing down the question and the steps for this one, okay? Just like when it was a table, we just switched the x and y. That's how you're going to start this problem. You're going to switch the x and y. So the x is going to come here, and the y is going to go here. So I'm going to rewrite it like this. And then I just have to solve it for y again, though, because whenever we have functions in algebra, we usually write y equals something, right? Because y is the output or the dependent variable. So we don't really want x to be the one by itself because x stands for input. So we're going to get y alone. So to remember how to do that, guys, it's just like solving an equation. Like we got to work backwards, do PEMDAS in reverse, which means you would need to add 5 to both sides. So on the right side, negative 5 plus 5 is 0. On the left side, you just have to write x plus 5 because we don't actually have like a value for x. So we can't do that math, right? And then to get y alone, get rid of the 3. Opposite of multiplication, you're going to divide everything by 3. So you could write it just like, now, key in there. I need to pause for a second. Did you notice that I said divide everything by 3? Okay, so like my fraction bar needs to go all the way across because we could actually write it separately if we wanted to. Like the x is getting divided by 3 and the 5 is getting divided by 3. Okay, you can even write it like 1/3 x means the same thing. So there's a couple different ways you could write that answer. It should take it like this on edge elastic or like this, either one. But again, if you're writing it as one fraction, that fraction bar has to go all the way across because both the x and 5, both terms are getting divided by 3. So again, if we were to take this and put it into y equals in our calculator and put this in y2 and graph them at the same time, guess what? You're going to see two functions that look like they're mirror images of each other over this line, okay? They would both be linear functions, but they would still look like they were flipped over that line because that's what happens with inverses, okay? So let's try another one. When I give you a function and if I ask you to find the inverse, here's the steps. You're going to switch the x and the y as step 1. And then you're going to resolve it for y. So think, how do I get y alone? The opposite of squaring something is to unsquare it or take the square root, right? Because that would cancel. Now, normally when we take the square root of something when we're solving equations, do you remember, a lot of us forget this a lot of times, but usually we have to put that plus or minus symbol when we do that. So just put your pencils down once you're done writing that note, because I'm going to talk to you why sometimes we're actually not going to put that, okay? So I just want you to listen on the next slide. Remember I told you on the last one we could graph both functions if we wanted. If I graph this and I graph this, I'm going to show you a picture of what it would look like on the next slide, okay? So y equals x squared, you should already hopefully know what that looks like is a parabola, right? So that is in blue here. That's y equals x squared. You're very familiar with it. Imagine trying to flip that over this line. Can you imagine how the red picture is like the mirror image of that, okay? So this is what the graph of this would look like because they have to be mirror images of each other over that line, okay? So here's the thing though. I want you to focus on that red graph. Do you, this right here. Do you remember back in the warm-up how I was reminding you of the definition of a function? That red graph is not a function because if I draw a vertical line, do you see how it touches the graph twice? Like we have the point 4, 2 on this graph, and we also have 4, -2. You can't have 4 paired with two things like that. That breaks the definition of a function. So sometimes, because we want all of our inverses to be functions, sometimes we won't put this anymore because it's like we're only going to look at this half of the graph right here. We want to kind of get rid of the bottom half. That will make it a function if we only look at that half of the graph, okay? So I'm going to go on to this for a second. You're going to notice, so this is the same problem we just did, okay? Remember, f of x is the same thing as y. So this is what we did in our problem a couple slides ago. We switched the x and y, and we took the square root, right? So now you're going to notice sometimes in the directions, it's going to say this. So if it says that, go back to thinking about y equals x squared. Normally it makes a whole parabola. But if you say that x has to be greater than or equal to 0, it's like we're not going to look at this half of the parabola anymore because over there the x's are negative, right? So if we only look at this half, flip that over the line y equals x, and now the answer would be a function, okay? So that just means, again, when we do our answer, a lot of times we're not going to put this because we don't want this half of the graph, which would be this. If we reflect it, we want it to be a function. So we're going to only look at sort of the positive half of the graph, okay? So just know that if it, like here, when we did this, now, if it says to let x be greater than or equal to 0, you're just not going to put that. You're just going to put this as your final answer, okay? So that's just, again, so that your answer will be a function, okay? All right, we're going to get into talking more a little bit about the vertical line test. So again, here's kind of what it says. If you lay your pencil down on a graph, or that would be the same thing as drawing a straight line. Maybe I should even use the line tool since I'm not very good at drawing a line. But if we take a straight line and draw it, it should, I still can't even draw it straight. This is terrible. You artists in here must be so critical of me. But if you draw a vertical line, it should only touch the graph once, right? All of these are functions, but not this one. Because do you see how when I draw a vertical line for that one, it touches the graph twice, okay? So out of all of these, this one is a function. It passes the vertical line test. If you draw a vertical line, it only touches the graph once. This one is a function. This one is not a function. And this one is a function again. You can draw a vertical line anywhere and it passes it, okay? Again, technically you did learn that in Algebra 1. But now that we're learning what inverses are, there's something called the horizontal line test. If you draw a horizontal line through a function and it only touches the graph twice, like this one did, what that means is that its inverse will not be a function, okay? So this graph right here, this first one, it's a function because it passes the vertical line test, but its inverse is not a function because it fails the horizontal line test. And that goes back to what we were actually talking about back on this slide, right? I'm going to clear this for a second. We said this one was a function, but if we flip it over the line, this thing was not a function, right? So this is kind of like a quick test to know if it passes the vertical line test, it's a function. But then if it passes the horizontal line test, its inverse will be a function, okay? So again, just kind of show you what that means. If I draw a horizontal line, this one touches it twice. That's no good. Here, I could draw a horizontal line anywhere, and it's only going to ever touch the graph one time. Same thing here. Same thing here. Like all those lines that I'm drawing, they only touch the graph once. But this one touched it twice, okay? So all of these, their inverse, if we actually found their inverse and made a picture of it, the inverse would be a function. However, the inverse of this one is not a function because we say it fails the horizontal line test. If you draw a horizontal line, it touches it more than once. So there's like, I have a slide here to summarize this, and I put it on your little formula sheet that I gave you for this chapter 2. The horizontal lines test says if you draw the inverse of a function f is also a function if the horizontal line only touches it one time, okay? So again, that function on the left is an example of something where its inverse would be a function. It only touches the graph once. The graph on the right, as we already said, its inverse is not going to be a function because it touches the graph twice. That's why, again, that problem we looked at earlier, sometimes we restrict it and only look at this part of the graph. That way, it would then pass the horizontal line test, and its inverse, which would look something like that, would then be a function, okay? All right, so what if we have a question that says, consider this function, determine whether its inverse is a function. So I have a picture of this graph for us already. We could go plug it in y equals, but I thought I would just go ahead and put the picture here already. So this thing is a function, okay, because it passes the vertical line test, only touches it once every time I draw a vertical line. But the question is, would its inverse be a function? So that means we have to check, does it pass the horizontal line test? So if I draw a horizontal line test, as long as it only touches the graph once at any point, and it does, then it's good. So you're going to say, determine whether its inverse is a function. Yes, it is. So then, since it is, it wants us to actually find the inverse. So we're going to take this. I want you guys to write it like this on your paper. I want you to put y instead of f of x. So remember our directions from earlier, how to find the inverse of something. You switch the x and y, and then you resolve it for y. So you got to think to yourself, how do I get y alone? So PEMDAS in reverse. So the first thing we would need to do is take away 1 on both sides. So we would have just the 2y to the third left over here. We have to just write x minus 1 on this side because, again, we don't have an actual number for x. Keep doing PEMDAS in reverse, right? Some people mess up at this point. After addition, subtraction, you got to do multiplication, division, meaning get rid of this 2. Again, everything over here has to get divided by 2. So make sure your fraction bar goes all the way across, okay? And then lastly, to get y alone, we'd have to do the opposite of third power, which we learned in this chapter means the third root or the cube root. So make sure you draw it going all the way over this whole thing. So like the answer looks like the cube root of this fraction. Now, instead of y, I'm going to teach you guys, remember function notation, but now that this is the inverse instead of f of x, this is what you're going to write, f with a little -1, but that's the symbol for inverse. So you read that, the inverse of f of x, okay? So if you ever see that f with a little -1, that's what it means. If f of x was this thing, f of -1x, or the inverse of f of x, equals this thing. One more time, if we were going to graph both of them, like if I put this into y equals, I already know it's going to look like this, okay? But if I graphed this one at the same time, guess what? It's going to look like it's flipped over this line. Remember the line y equals x? So I could try to sketch it. I'm so bad, though. It would probably look something, I can't even do it. Never mind. I'm not even going to attempt. Try to imagine in your brain what it would look like if you flipped it over that line. That's what you would see, okay? All right, so a lot of my questions so far have been like, I gave you a function and asked you to find its inverse. What if I give you two functions and ask you if there are inverses of each other or not? Well, here's how you would find out, and this is something you're going to want to write down in your notes. How do you know if two functions are inverses? Remember when we learned composition functions the other day, where you like take a function and put it into another function? So if I give you a function f of x and g of x, and I want to know if they're inverses, what you're going to have to do is f of g of x, but then you also have to do g of f of x, and they both should come out to be just x when you do that, okay? Again, you'll see what I mean in a second. You just want to get that written down for right now. So verify that f of x equals 3x minus 5 and f inverse of x equals 1/3 x plus 5/3. Okay, so we're going to have to take f of f inverse of x, which means we're going to take that and fill it in here, but then we'll have to do it the other way around too. Okay, so let's do it the first way. So I would write this out here like 3 times. We're not going to put x, right? Because remember, in place of x, you're going to put this. So 1/3 x plus 5/3. Let's just write it out the other way too before we do any math. So this one says take f of x and fill it into this one this time. So again, I would recommend writing this out, but where the x was, you're putting this, right? 3x minus 5. So you're putting one function into the other function. Let's look at the left side of this. So you would have to distribute 3 times 1/3. So some of you might need your calculator for that. If you do, that's fine. It will just be 1. I'll tell you why, because think of this as like 3/1. 3 times 1 and 1 times 3 is like 3/3. It's just 1. And so then you have to do 3 times 5/3 as well. And that should just give you 5 when you do that. Again, if you need your calculator, that's fine. Do what you need to do. Don't forget to, don't lose that -5 though. So now we have a +5 and a -5. Like 5 minus 5 is just 0, right? This is going to end up just being 1x or x. That's good so far because that's what we said. When we do f of g of x, it has to equal x. But now we have to check g of f of x too because they both have to equal x. So let's go over to this one. 1/3 times 3 is again going to give us 1x. We don't really need the 1. And then 1/3 times -5. If depending how you type that in your calculator, you might get a decimal. You need to just leave it in fraction form. So math bracket. Don't forget about the plus 5/3. So now again, -5/3 plus 5/3 is 0. We're just going to end up with x again. So we know that they are inverses of each other because we got x both ways, okay? Let's try another one. See if these ones are inverses. So again, we would have to do f of g of x, but then we'd also have to do g of f of x. So let's work with f of g of x. That means we're going to take the g of x, remember you kind of read it from the inside out, and fill it into this one. So it would look like x plus 12 was f of x, but you're going to fill in this, right? So in this one, guys, you don't really need parentheses because it's like a 1. 1 times x is 1x, and 1 times -12 is -12. But then -12 plus 12, that's going to cancel out, right? You're just going to be left with x. So far, so good. G of f of x means now, so read it from the inside out, the f of x is going to get put into g of x. So I would write out g of x, x minus 12, except we're not going to be putting x, right? We're going to be filling in what f of x is, x plus 12. Once again, you don't really need the parentheses because it's kind of like a 1 times everything. That wouldn't change anything. 12 minus 12 is 0, right? So once again, you're just going to be left with x. So it said, see if these are inverses. Yes, they are. Okay, since we got x for both of them. Questions on that so far at all? Okay, see if these ones are inverses. So I'm going to let you start this one yourself this time. So you find f of g of x for me. See if it equals x. If it does, go on and find g of f of x, because remember, you have to get x for both of them in order for them to be inverses. So f of g of x, I'm going to take this and fill it in here. So I'm going to write out 2x plus 4, except where x is, I'm filling this in, right? -2x minus 4. So I'm going to need to distribute 2 times -2 is -4x. 2 times -4 is -8. Don't forget about the plus 4. -8 plus 4 is -4. And that's as much as we can simplify. It doesn't equal x. So we really don't even need to go on and find g of x because we already know the answer is no, because we have to get x for both of them. Okay, so if we already know it's no, there's no point in going on. Questions on that at all? Okay, so we're just going to kind of do a couple more quick. Oh, I forgot one more like this. See if these are inverses. I know it says try on your own, but this one's a little weird. If we want f of g of x, we're going to take this whole thing and fill it in here. So copy this carefully. Like, again, I would rewrite this, except where the x is, you're going to fill in this, right? The cube root of x minus 9. So this is where you have to really think about some things that we learned earlier in the chapter. If you take the cube root of something, but then raise it to the third power, those are like inverses of each other. Like you're just going to be left with x minus 9 because the cube root and the cube cancel each other. And then you have the plus 9 though. So -9 plus 9 is 0. You are just going to be left with x for that. Okay, and then let's write out what it would look like. We have to go on, right, because we have to check if it works the other way. Is g of f of x also equal to x? So this time we got to take this and fill it in where this x is. So again, I would write this all out, the cube root of x minus 9, but where this x was, we're filling in x to the third plus 9. So this time, you might want to, again, imagine like there's a 1 here. If you distribute 1, it doesn't change anything, though, so we don't really need those parentheses. So here's the thing. 9 minus 9 is 0, so we would end up just with this. But same thing as we talked about on the left, the cube root of something cubed would just be that something. Like the third root and the third power cancel each other. They're inverses. So you just have x. So yes, these are inverses. Questions on that type of a problem at all? Okay, so we talked about like 3 different types of problems. So if you have to know if something's inverses, you have to check f of g of x and g of f of x and see if you get x for both. We learned how to tell if something is a function and how to tell if its inverse is a function. So I want you guys to, we're going to just do a couple questions to finish here before you start your homework. I want you to go graph this in y equals and see what it looks like. And once you do, you should see something that reminds us of a parabola. That can still happen even when it's a 4th degree function. So the question is that a function? So remember, that's where you need to think, does it pass the vertical line test? Like anytime I draw a vertical line, does it only touch the graph once? And the answer would be yes, okay? So then we want to know, is its inverse a function? Now that means, remember, it would have to pass the horizontal line test. And it doesn't, because if I draw a horizontal line test, it touches twice. So the answer would be no for that, okay? So remember, you don't even have to actually find the inverse or anything like that. We already know that it's not a function if the original function does not pass the horizontal line test, okay? And then last type of problem we looked at, remember, is how to actually find the inverse. So remember, step 1, switch the x and the y, and then resolve it for y. Get the y alone. So you go ahead and do that real quick. We would need to take away 10 on both sides. So you would get y squared equals x minus 10. And then remember, when you take the square root, oftentimes we put that plus or minus. Now I'm going to remind you in a second why we don't do that, okay? So this should be the answer. So here's the thing, okay? If I graph this in y1 in my calculator, it's going to look like this normally, okay? But because it says x has to be greater than or equal to 0, that kind of means like we get rid of this side of the graph because the x's are negative over there, and it says x has to be greater than or equal to 0. So I'm only looking at that part of the graph. Imagine flipping that over the line y equals x. I'm going to do my best to show what it would look like if we had the mirror image of that. It's probably going to look something like that, okay? So that's why we don't want this half of the graph. Normally, that's technically what the whole thing would look like if we had this symbol. But because we started with only this half of the graph, we only want this half in its inverse, so we're not going to put the plus or minus symbol. That's all because of this thing, okay? That way our answer will be a function. Because again, if I graph the whole thing, it's not a function. It doesn't pass the vertical line test, okay?